welcome everyone. Thank you for coming. This presentation actually goes back a really long time because 11 years ago I was sitting down there by the cameras, and this is my colleague David who was presenting at the time, and we were doing Hadoop. That was a really cool thing 10 years ago, most successful cargo cult ever. And we held this presentation of how we improved the life for Hadoop developers. What actually should have been the title was how we democratized data at Spotify, because the work that we did back then was really successful in spreading the use of data throughout the company. To a very large scale, you've seen like Airflow dependency graphs and so forth. This is a dependency graph from those times. It has about 2,000-ish nodes. And this is the last time the full dependency graph of Spotify was recorded, as far as I know. We got a receipt 8 months later of what we were trying to achieve. We were trying to make all the teams in the company like enabled to innovate with data. And 8 months later, this feature called Discover Weekly was launched. It's one of the most popular features at Spotify. And when the people that did this went on a presentation and they said we could do this because the company had enabled bottom-up innovation. In an ordinary company, this had taken like a C-level decision and 50 engineers for a year. We did it 3 people, first version in 3 weeks. This was the CEO didn't like it. He tried to kill it, but they just didn't get any resources. They launched it anyway, and within 1 year they had 40 million. Active users. So it's arguably one of the most successful machine learning features ever built by a European company. So I'm super proud to have contributed a little to this. And when I saw this, I feel like this is something that all companies should have, right? Why only some? And I've tried ever since to spread this kind of capabilities, which is really rare. To the outside world. Fast forward a few more years, I was sitting over in the Kessel House, and I was sitting next to one of the other veteran or recurring presenters, Niels Bashes of Bol.com. And there was these people showing on stage. They had a whole bunch of pipelines, and they had refactored and re-architected things. And the most interesting thing was at the end, because they had this graph. This is not the graph. This is just slop. And at the end, they said, okay, they got the question, okay, for this graph with like 20 jobs or something and 50 nodes, something, how many people are involved? Well, it's about 30 people working on developing these pipelines. And what I didn't tell you before is that the graph over here, this was before we democratized data. This was just a few teams doing this. So there you see the 2 orders of magnitude difference. And I asked Niels, this 1 person, 1 pipeline, 1 person a job, is that a normal ratio? And he was like, no, this is way orders of magnitude off. Somebody needs to explain this. And Niels, if you're listening to the recording out there, I'm trying, I'm doing my best. This is nothing to be ashamed of, because 1 person per pipeline, 1 person per job is actually a really common ratio. There's this idea in not only in data, but in all of IT that we're roughly equally good, everyone. And then there are some that are really good. They're probably twice as good or 10 times as good. But if you measure metrics, there are actually many orders of magnitude in difference in KPIs and how often you deploy and how time to recovery and so forth. There was these DORA metrics that are presented in the State of DevOps report, and they show that for typical productivity metrics, there's a span of like 1,000 times between the laggers and the leaders. But in our own bubble, we think that it looks like this, right? And I've been lucky to work on a couple of companies that are really out in the sort of far out tail there on some things. A couple of years before I worked at Spotify, I worked at Google, and they are really, really good at some other things. But they are crap at some things that Spotify happens to be really good at. And I was like, they're 2 super successful companies that have huge missed opportunities here. That must mean that everyone has these huge missed opportunities that if they could just improve, like there are orders of magnitude in efficiency to gain. So how many people heard of the Spotify model? A few. That's usually in the non-data conferences, like usually everybody raises their hand. That has nothing to do with data, but it's a sort of agile working model that people have came to copy. And it has become known because they were really good communicators. But what we realized that the things that led us to have like 2,000 jobs for 30 developers, which I'm sorry that I can't take any credit for that because that happened before I worked there. The things that we got right to get there have not been communicated because we didn't have anybody that could communicate this well. So I've been trying to sort of compensate for that going forward, and much of the work I've done is been spreading sort of the practices that were successful, but it's not my role anymore to say how Spotify works because they have diverged in different directions. So what I do is more similar to, and what I describe here is more similar to what they did like 10-ish years ago. Now we're getting closer to the paradigms here because I've on various occasions tried to figure out what is it that we sort of ended up doing that was efficient. And we didn't do this with a plan. It was things that happened out of accident. And if there are more dimensions than this, but this is a technical conference, so I've tried to sort of enumerate the technical dimensions where there are reasonable choices to make in how you work. But we ended up having a very firm choice in these 7 dimensions. And I'm saying how you work because at the time, we were dabbling with Hadoop and Spark and so on. We thought about it was technology. That turns out to be mostly irrelevant. It is how you work with the technology that I found matter much more. We were inspired at the time of Nathan Mars's work here, where he's most famous for the Lambda architecture, where he sort of explained that, you should do this functional programming style, but in data architecture. And that was something that we sometimes explicitly used, but also got pushed into because we were using Hadoop, and that's sort of the only way that you can use Hadoop. This is a blog post by Alex Beauchemin, who created Airflow. A few years later, he called it functional data engineering, and I guess that's the best term so far of describing these work patterns. We ended up adding a few things or making a few choices ourselves by coming much from the Scandinavian culture. We had a strong culture of cutting out everything that wasn't necessarily. The fewer things, the better. And there was also a strong agile culture, which led to the pool-based work down there. So, what I realized is that there are many different paradigms on how to work with data. And these paradigms have made different choices in these 7 dimensions. And kind of which you choose end up affecting your work for good or for bad. And depending on your use cases, there's no single best way of working. And I'm going to go through these paradigms from the view of the dimensions to see how they affect your practical work, in particular your operations. And I'm not even going to try to be neutral here and say, there are pros and cons, because I've even fallen in love with these choices that we made. So I'm going to try to explain why they were made as successful at the time and have done so in the work that I've done after Spotify. So you have to bear with me there. One point, these are all paradigms. They are sometimes related word-wise to products, but these are not the same thing, right? So data warehousing is a way of working and a paradigm. Data warehouse is a product. A data warehouse typically includes data warehousing things, but also other things, right? So don't confuse these. All right, we start out with from the top. The way that we had to work with Hadoop was to build data pipelines. And that's also common in other paradigms, in data warehousing, stream processing, and so forth. And the pipelines go in one direction, right? Data comes in here and it goes downstream. Whereas if you integrate things with microservices, they go in all sorts of directions. This has impact on operations. What do I mean with operations? Well, that is a expression that covers a lot. I'm going to touch on some of these, which I think are sort of typical operational maneuvers. Create a new thing, roll out a new version of that thing, recover from that the thing crashed, and recover from that the thing produced bad data. And I'm not going to go through the full matrix here, but I'll pick up examples from there. I will mostly skip the create the new thing, because in every tool blog post that's typically trivial you learn, but it's the things further down that are hard. If you have a bidirectional environment, and you roll out a new version, then you need to take some care, right? Because now, as soon as you roll it out, it's going to hit, real traffic is going to hit it, and it's going to have real impact on your users. So you typically do this kind of carefully, maybe a few users at a time and so on, and you spend a lot of time doing QA to figure out that this is kind of safe. If you have a one-directional paradigm instead, you can do parallel things. So that you can, if you want to be careful, you can do things in parallel and then compare the results, which is much more difficult here, because here, unless you have some specialized constructs, you typically need to expose them to real traffic. And it's the same thing if you're doing batch, like with the functional data engineering paradigm. You can roll out separate pipelines, and in this case, they might hit the user quickly. In this case, they will hit the user later. This saves us a whole bunch of carefulness and QA. Now, if we have a scenario where the rollout goes bad, then we have a very different situation. Because if this contains a bug that spreads bad data throughout the system, it will instantly spread in your system in various directions. And which directions is challenging to figure out, because then you need to look at the code and the logic and various details. I held a similar presentation a while ago, and I asked the audience, have you had any of those days? And the audience nods, right? And I asked the audience, was it a good day? And someone at the back with a heavy Eastern European accent said, it was a normal day. So they were used to it. Right? If you have a one-directional data processing paradigm, then the bad data goes in one direction. So you have some limited scope of where to look for the bad data and where to figure out how to sort of remedy from that situation. And the same with data pipelines or in a data lake paradigm. So this saves you a lot of time in terms of recovering from things. These two are quite different, streaming and batch processing, for reasons that we will get to. Namely that one of them is online and things happen immediately, whereas in batch processing things happen offline. You take the data and you store it for a while and you process it in peace and quiet, and then later you throw it out for use. So, but most businesses need some kind of online activities, right? Otherwise, we could only interface with them via like email or something. So, in order to have the benefits of the offline world, you need to have borders between offline and online, and those borders you typically need to be quite careful in when you hand things off, because these worlds work differently. And you can sort of harm both worlds if you do it poorly. I have some war stories about that a Hadoop cluster turns out to be a great internal distributed denial of service attack on the online databases if you just point them in the right direction. I've taken down 2 different login services in that way. So, and then when you have computed something with the offline, you typically do a very careful handoff to the online world again and say, here's something precious I have for you to pick up. And the reason that we shift is that we can move much faster in the offline world because we must need to be less careful. We can deploy faster and innovate faster and so on and so forth. Now, if you don't think, what paradigms should I use? Then what usually happens is that your system just grows, right? We had all of the autonomous teams, and they can use whatever technology they want, and you get this like organic mishmash. Some people are nodding. I see you've seen that before. Which means that we have lots of these borders between the paradigms, which I just said are like some kind of operational risk where you have to be careful. One of the things we were lucky with is that if you adopt Hadoop, you have a Hadoop cluster, and you only want one Hadoop cluster because they're really expensive to operate. So we ended up throwing all of our data processing in there, which like democratized things and made things very homogeneous. This was purely by luck and accident. Now we're past the Hadoop age, so you don't have that luck anymore, right? You can use wherever you want in the cloud, which is great, but the homogeneity in itself has a value. So looking a bit closer at the error scenarios here, if you're doing the functional data engineering, is if something happens, you have bad code produced a bug, you figure out the bug, it's going bad out there, you ship new code, and then, depending on your tooling, it can either automatically backfill or you need to kick it a bit. It says backfill is automatically easy here. Depending on the workflow orchestrator that you use, you may need to give it a kick, because Luigi is an example of an asset-based workflow orchestrator, which looks at the data sets that exist. Airflow is an example of a task-based workflow orchestrator that remembers what things have been executed, so you need to give it a kick in order to do the recomputation. And this works for even larger scenarios, as long as you stay within this offline world, right? To illustrate that if you stay in one paradigm, you get a whole bunch of operational benefits. This is what we used to do back in the day. We used to remove the data sets that were faulty. Then we realized that there's a simple tweak here we can do to even sort of strengthen the process even more. We don't remove things, we just version them, and then we bump the version whenever something was wrong. And this turns out to be beneficial for downstream, because many bugs downstream don't care about, but except for financial reporting. They care a lot about these bugs, but recommendations and so forth. So you can give downstream a choice to recompute everything or not to recompute everything. I call this the frozen lake because in this model, which is sort of similar to the data lake processing model, we just never, ever remove anything, except that to sort of save space in the end. Right, but stream processing is online. So if you have some of these scenarios, you don't no longer have like dozens of data sets that were wrong that you can go and enumerate and say, okay, these 20 data sets were bad. Now you have tens of millions of events instead that sort of went downstream. And you need to figure out, okay, how do I recover from this downstream? And here's the answer. This is a blog post by Confluent that sort of does the thing that I did on the last slide, but page after page after page after page with instructions. And it actually doesn't cover this case because it only covers these small cases here. So that illustrates like the difference between online and offline recovery, even though you're in one direction. Immutability. In an immutable paradigm, the things that you write are frozen. You never ever change them. In immutable paradigm, you update things. And this is the main difference between functional data engineering and data warehousing, where in the data warehousing model, you run a job and you update the tables instead of producing new immutable data sets. Stream processing is kind of in between here, because the facts that you put in the stream, they are frozen, but the whole view of things in the stream, all of the orders so far, that's a dynamic thing. So this is the main, as I said, the main difference between data warehousing and functional data engineering. Data warehousing, you run processes on a regular basis, and they upload these downstream tables, which kind of draw most of the time we draw the dependency graph the same, to some kind of normalized, data vault, star schema, satellite schema, whatever, which is then read in the read path, this normalized schema to be used for whatever. Because these things are mutable, it's a bit challenging to share them if you've computed things that are valuable for many teams. Because you need to synchronize on how they are updated, what the semantics are, what the sort of time labeling on the data is, and so on and so forth. And also this normalized model, that's kind of a pet. That's not something that you easily share or easily change. And if you look in classic data warehousing literature, it's full of, really think beforehand so that you don't make mistakes here with slowly changing dimension and so forth, because that's going to be really hard to change later. In the immutable world, instead, we create new partitions here. And this is what sort of Hadoop forces us to do, because if you use MapReduce, which was the hot thing at the time, then this is the only option that you have. Now, that turned out to be a blessing in disguise, because once these data sets are written here, they can be read by anyone. That does not have to speak with the producer. And that's important, because human interaction makes you slow. If you need to wait for a human to find a meaning or blah, 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 it takes eons. So we've had situations where we finally decided to, okay, let's remove this pipeline. It's probably not worth anymore. And it was actually used for 200 downstream jobs. Some people I tell that say, oh, governance, I'm scared, right? And some people say, wow, that's a lot of business value that was generated with minimal friction. Now, the drawback here is that you need to explicitly address the partitions. If you say, I want all of the orders, here you get all of the orders because they're in one table. But now you need to say, what do you mean with all the orders? Which partitions do you need? When things go wrong here, if you have a bug here, then it will taint the tables downstream, and those tables will be bad. And the naive solution is to recompute all of the history, which is not great, or you have a challenge. You have a challenge ahead of you to figure out what to recompute or not. In this case, we know from the dependency graph which partitions were tainted and which were not. So we have tooling that tells us precisely what went wrong and what did not go wrong, or at least the information is there. We got Hadoop by cargo culting Google. A few years later, we got the modern data warehousing, which was invented at Google. And in that case, there's no right path. In this paradigm, there's no right path. You don't have these ETL jobs that produce things to tables. You instead store the raw data, and you have super powerful data warehouses here that go and compute all the things that you need on the read path instead. And that is great in many ways. It allows for super fast iterations. When you have a new idea, and with these data warehouses, you can test out these new ideas real fast, even faster than the functional data engineering case. But it comes at a high compute cost. So sometimes it's good, sometimes that's not worth it. I have some war stories, financial war stories here as well, but I'll spare those for a later moment. The One of the things that we needed to do in order for these things to work was to make metadata management explicit. And what I mean with metadata management is dependencies, as we've touched a bit, but also schemas. There are also other types of relevant metadata. And by explicit, I mean write them in code, commit them in code, so that they are very well defined. Whereas in other paradigms, for example, in data warehousing, if you work with databases, the metadata around schemas tend to be sort of implicitly stored in relational tables that are in effect defined by your SQL statements, which are in the middle of your business logic. Making metadata explicit is a way to separate your business logic challenges from the system-related superficial challenges that pop up, whether you like it or not. So this is an example from the Swedish health authorities in the COVID times. And every day they would show this graph that was pointing down, so you could think that the pandemic is now over. Somebody pointed out in the far graph here, there on the right that, guys, this graph points down every day. You're not helping us by showing it, right? And we all understand that this is probably due to delayed data collection, right? That's a common problem that can lead to interesting anomalies like this in your graphs, or like this if you're missing some data around midnight every day. And this is when your sort of business logic somehow gets mixed up with your managing the artifacts of your system or of the real IT world out there. And the tool that we use to sort of separate these two things is the workflow orchestrator. Which separates the business logic from the managing all of the delays and the dependencies and so forth by ripping them out and storing them and defining them separately. This to the left here is Databricks. There is like a workflow manager or something like that. This is not a workflow orchestrator. I want to point that out because this just says please run these tasks. You could do that in the bash script. This will run every time identically. The only difference is that there will be new data there every time. The workflow orchestrators, they define dependencies between the time partitions and the job that generates the time partitions. This is from Airflow. And usually we have a dependency graph that looks like this, which kind of looks like that one, because we usually flatten out all of the time dependencies and don't care about them for good reasons. But it will run with different parameters on every run, which you don't do in this sort of data warehousing world, where you just run with whatever happens to be in your tables. This is a Luigi snapshot, and that's one of the few tools that I know that actually draw the full dependencies between the time partitions with sort of time awareness. Then, on the other hand, the graphs can grow quite big. Then I want to sort of make this distinction here. And this is what it can look like. And this in this case, Luigi code, but I think it would look similar in other workflow orchestrators as well. That you explicitly say, here, I'm going to form a session here, and I want a window back in time that is 4 hours to look at my session. Sessions is an interesting example, because for most definitions of a session, you actually need infinite time in order to make that reproducible. So this is like an important parameter to say how much time back do I want for this window. Defining code, right? The dependencies. And you remember that frozen lake I told you about? It's here. That's the only difference. We put a version here in these numbers, and we've sort of snapped the paradigm a little bit. That's easy to do if you use tools that are not too strongly opinionated, where you can build your own abstractions on top of them. So, in functional data engineering, we use these workflow orchestrators to to explicitly define our dependencies. And we do need to sort of handle these dependencies anyway if we're in another paradigm. But we have to do so without the tool and within our business logic. So in data warehousing, unless you want to compute everything, you can have some kind of arrival time field and select the partitions, or you can have a watermark table that says these are the things that happened since last time, and so on and so forth. But there are challenges when this grows complex, and with this, when you combine multiple pipelines and so on and so forth. We were lucky here because we sort of figured this out early. Also, I can't take the credit here. This was already in place when I joined there. But we happened to make this innovation, and this was really one of the key factors. Getting this right was one of the key factors between the success we had. Let me save some time and skip schemas. So, well, one of the other things that we got right was that we were working from a very much software engineering culture, and then made it natural to use the native tools and not specialized data tools, because we didn't have much expertise in like BI development and so on and so forth. And that turned out to be very successful because it integrated well with not only solving insights challenges, but also production challenges and machine learning and so on and so forth. In particular, we did not use SQL for data processing. And this is something where I see that if you have a particular specialized tool, people come in the mindset of what can I do with this tool rather than what can I do with data, and that sort of limits the scope of the things that they work with. If you take it from a software engineering perspective, you might want all of these things in order to scale up and build better things and so on and so forth. But SQL does fall short on most of them. The main reason and the main factor for using SQL is that people know it, which is a relevant and good factor. And if you want examples, I have this Twitter rant from a number of years ago with some more specific examples. One concrete example of why it didn't work out was that we actually tried for one of our larger pipelines, which was a master data management thing. And in this case, we came from the use case, right? We didn't come from SQL and say, okay, what can we do with SQL? We had the working use case, and we were thinking, we were trying to leave Python MapReduce, which seemed like a losing proposition at the moment. So we tried to implement this, and it really didn't work. We would have to sacrifice tons and tons of things, including performance and data quality measurements and so on and so forth. So clearly, for our use case, it didn't cut the deal. Unix philosophy is the idea that you do one thing well. Every component does one thing well and keeps a small scope, which the data vendors really don't want you to do. They want you to use their thing for all of the things. So this is, if you listen to the vendors, you will never follow this this advice or this philosophy. The one example here is that we didn't buy the vendor stuff and say, oh, okay, we're all going to go all in with Databricks or Snowflake or Cloudera or whatever. We instead sort of control the mortar and build the little things or took little pieces and welded them together by ourselves. And this enables evolution because it's easy to pick out one of the things and remove it with something better. And this is an example. At the time, Docker was too immature. We evaluated it. It was too immature. So we built our own poor man's container. Fast forward a year or two, Docker was mature. We could throw that out and replace it with Docker. Fast forward a couple of years, Kubernetes came. We could throw Docker out and replace it with Kubernetes and so forth. This has been a philosophy that I've tried to keep to and stick to in order to be able to sort of evolve and improve quickly. Another aspect of Unix philosophy that I've learned is the separate separating computation from integration. These are two different things that fail for different reasons, and therefore you are a lot better off if you separate them into different jobs and different activities. That makes the operational aspects a whole lot easier. The last piece is related more perhaps to organizing and ways of working. And we had a strong agile culture at the time. And therefore, it was natural to sort of only do things that were asked for. A lot of literature centered around data products and data mesh and so forth actually preach the opposite, like the producers should produce these things, and then the consumers will happily consume them. And they often struggle with the feedback loop there and getting the producers to produce the right thing for the consumers. From a technical aspect, it can look sort of like this: that in many cases, like the sessions we had before, there are parameters that you need to choose. But as if the producer chooses them, he or she will make a decision for everyone downstream, which may or may not be correct. So if you instead switch it so that the consumers can choose these parameters from upstream, which you can if all of these things are defined in code and you can access them via the workflow orchestration, then you can have one or many of these as needed without forcing your decisions on the consumers. So, looking back here, I think I've probably forgotten a few of these, to cover a few of these. Some of the popular ones is Lakehouse, which conceptually is the same thing as a data warehouse, except that it's done on different technology. Beam is an interesting thing where Google has their own version of combining data processing and batch processing, and I haven't really understood how they manage the dependencies in the aspects that I've speak about, so I won't speak too much about it. But I hope I've covered at least the important paradigms here from an operational perspective. And I've followed these 7 choices in the last decade or so and managed to, in terms of KPIs, get to the levels that we were at Spotify. This is an example from an enterprise engagement. And this is all of the operational pipelines for about 10 million something consumer-facing units of something. And we managed to build this graph on just 2 people over a couple of years. And if you multiply that by 20, you get sort of the same magnitude as a Spotify graph. So we figured out how to sort of replicate the technical success we had and the productivity we had, but without the hundreds of person years of investment that Spotify has in the data processing environment. So I've been spending a lot of time with the enterprises these last few years and trying to help them to sort of adopt these paradigms. And that is kind of tough, mostly because of cultural reasons. And I'm really annoyed that they have these like 1 person per pipeline teams. And I'm saying, you could do 100 times better. You do something really important here. I would like to help you, but that's really difficult. Now, if we look in the other direction and say, okay, where the leaders here? Well, Google's are several orders of magnitude ahead, right? Even compared to the best European companies. And all of the ones, Google is furthest out there in the tail in terms of data. And the rest, and they're followed by a whole bunch of Americans. And this annoys me a bit. I think we hopefully can do better. And if we want to, I think we must lift ourselves above pipelines and jobs and so on and so forth. Because in the last 15 years, this capabilities of workflow orchestrators has been more or less the same. And all of the innovation has gone on convenience and making it easier for beginners to adopt these things, but not necessarily better for software engineers. The modern ones are harder to build on top of because they have all of the UIs and the convenience and the nice annotations and so on and so forth. So I hope that we can innovate here, and because we can't do like 1 billion data sets per day with pipelines and jobs, like we need to get further. So a bit fragmented. I hope that you have like gotten a new light on how you think about operations and processing, and so on and so forth. And there are a few main paradigms that have, and then there's a latency versus productivity trade-off here, which is why I tend to choose slow batch processing, because it really cuts down the operations and the innovation, thereby the innovation speed. Data warehousing will be around for a very long time, but I think that its only USP is that it doesn't require software engineers. If you have sufficient software engineers, I think that's a paradigm sort of to leave behind to the 90s. And data engineering has become kind of a muddled field, because I'm one of the veterans from the Hadoop era, and I have no competence in common with people that do BI, used to call themselves BI developers, but now also call themselves data engineers. So we have added a little confusion there. So I hope that this information that I produced help you reject what the vendors spoon feed you, the American vendors, and help us so that we can like build European competence here in these fields and slowly become a little more sovereign, because the vendors, they don't want you to succeed. They want you to do lots of things with few people. They want you to do some things with many people, because that generates their revenue. So think for yourself, make your own decisions. I hope I've helped a little bit on those decisions. Thank you.
Yeah, Lars, thank you very much. Any questions?
Hey, thank you. Great talk. On one slide, I saw you flash very quickly that premature modeling is a waste. And I wanted to ask, also, since you mentioned that in the functional approach, we should focus more on consumers, so data products with a use case. How does that go together? Can you elaborate on that, please?
So now you forced me to do some of the slides that I skipped because I was slower than usual. I'll take these three then very quickly. Right, one of the things of being one of the properties of being consumer-oriented is that you move away from producing these heavyweight data assets like pets. Like if you work with knowledge graph, it's often the knowledge graph that's a pet. Like I used to work in a company like 15 years ago, and they have the knowledge graph. And forward 15 years, there's only this one same knowledge graph. I was part of another journey where we moved from here to factory of knowledge graphs, where we changed so that the downstream users could produce their own knowledge graphs based on code that was reused instead. And then we can have many models. So this is a turning things into factories so that they become cattle. And you can apply the same reason on machine learning and machine learning models, right? It's not the model, it's the factory to generate the models. And this is part of sort of Google's machine learning maturity journey. And that means that the modeling that we do for the data warehouse is careful modeling and so forth, and careful building on the knowledge graph or the model. That's ways to do super carefully. Instead, if we spend time on making it really easy to regenerate these things when they are needed, then we can move much faster. So data modeling is no longer a first-class citizen for a good reason. Right? We do need modeling, but we don't need to do it waterfall model anymore.
Thank you. Yeah, just a quick. I mean, you seem to not like SQL, and I mean, BigQuery makes it. If the resulting table is in BigQuery, it's a bit awkward to process the data with other tools. Do you tend to use cloud storage and file for your tables and Iceberg or Parquet, or how do you tend to store the data in between these graphs?
Well, the storage is like not so relevant to the paradigms, right? When you say if your data happens to be in BigQuery, well, that's a choice you've made. Yeah. I like SQL for interactive exploration. That's really where it shines, and that's the only thing it was intended for originally. right? We've just used it for some other things. But copying things from one storage to another is a really cheap thing to do, in general. And so so we look at for every step that we do, we can look at and see what things do we need from storage. And if in the data lake paradigm, we need sort of nothing from the storage, so we take whatever is cheapest, which is blob storage. In the online world, we need much more things from the storage. We might need super fast access. We might need geo lookups, and so in that case, we will use Postgres. We might need super scalability, so we might use Cassandra and so forth. So it tends to be that the offline world that have very low non-functional requirements, we use whatever is cheapest. In the online world that has stringent non-functional requirements, we adapt the storage to those requirements. And if in the offline world you can choose whatever. If you store it in BigQuery, you're paying a lot of money, but in comparison to blob storage. But that's your choice.
Lars, thank you very much. So give him a big applause.